Hello and welcome back to my YouTube channel. My name is Professor Kovala, and today I'm going to be talking to you about the high frequency small signal analysis of a common source amplifier using Miller's effect. And essentially the goal of this video is to find the AV gain of the common source amplifier here located to the left, which is basically the V out over the V in. And we're going to approximate this AV gain using something called the Miller's effect. And I would recommend the viewer to check out a video that I made called "What is the Miller's effect? Clearly explained," in order to really grasp the concept before continuing with this video. So in the past, we've proven that if you have a common source amplifier similar to the one located here on the left, you can map it to this type of MOSFET configuration, understanding that CGD experiences Miller's effect, and we could split CGD into two different capacitors. At our input, we have this CGD 1 plus GMRD, and at our output, we have this CGD 1 plus 1 over GMRD, where again, GMRD is the AV gain of an ideal common source amplifier. And when I say ideal here, I mean in the sense that there are no parasitic capacitors, okay? And there's no channel length modulation. So for example, RO is equals to infinity. And my source located here is connected to ground. So there is no source degeneration. Okay, so let's go ahead and draw the small signal model of this common source amplifier and analyze it considering Miller's effect. Okay, so given the small signal analysis here, let's go ahead and analyze the circuit. And what I'm going to do first is I'm going to say that this here, I'm going to consider as C1. And this here, I'm going to consider as C2. So let me go ahead and write that to the right-hand side and clean this up. So then the next thing I'm going to do is I'm going to label this node here as my voltage V1 and this node here as my voltage V out. I'm going to erase this because it might be a bit confusing, but essentially V out is just the drop over RD and C2. And what I'm going to do now is I'm going to label some currents. So if we can imagine this entire node here is V out, so that means that the current leaving here is I1, I2, and I3. And what I'm going to write is a KCL at V out. This can also be called nodal analysis, right? So essentially, this becomes I1 plus I2 plus I3 has to equate to 0. I1, we can see that it's GM V1. I2 is the voltage V out times C2 times S. So I'm writing this in the S domain, plus V out over RD has to equate to 0. And this is essentially my equation number 1. And then to solve for V1 here, we can say then that we're going to use voltage division or voltage divider at V1. But as you can see, this is essentially a low pass filter. Okay. For example, low frequencies will pass through, but high frequencies will go straight down to ground because this is a short. A capacitor is a short in high frequencies. I hope that makes sense. But essentially, we can solve for V1 by saying V1 is equals to the impedance across the capacitor divided by the impedance of the capacitor plus the impedance of the resistor times my voltage input. So again, the capacitor impedance is going to be 1 over C1 times S over 1 over C1 times S plus R times Vn. If I go ahead and multiply numerator and denominator by C1S over C1S, I am going to get Vn over 1 plus C1 RG times S, making my equation number 2. So again, let's just note the goal of the analysis is we want to eliminate V1 and find V out in terms of V in. So this here is my goal. So essentially what you can imagine is we can take this here and plug it into here, and then we'll have V1 and V out in this equation number 1, so we can solve for V out over V in. With that being said, let's go ahead and plug V1 into equation 1. What I'm going to get is this GM V in over 1 plus C1 RG times S plus V out C2S plus V out over RD has to equate to 0. What I'll do is I'll multiply both sides by 1 plus C1 RGS over GM. So then what I get is this V in, because again, GM cancels out here and 1 plus C1 RGS cancels out there. So I'm just left with V in. This is equated to, I'm going to move these two to the right hand side. So it's going to be minus V out times C2S times 1 plus C1 RGS over GM plus 1 over RD times 1 plus C1 RGS over GM. And essentially I want to get a common denominator to be RDGM. So what I can do is I can say then that V in is equals to minus V out. In order to get RD into this denominator, I can write, and I'm going to go ahead and distribute my C2S as well. So then this becomes C2 RDS plus C2 C1 RG RD times S squared. And then I get my GMRD plus 1 plus C1 RGS over GMRD. So now I can write that, therefore, my V out over V in is equated to minus GMRD. And then I get in my denominator C2 C1 RGRD S squared, which again is this term right here, plus C2 RD plus C1 RG times S, which satisfies this and this. And then lastly, I just get plus 1. Okay, so this looks like a clean equation. So let's go ahead and now plug in C2 and C1 and make it nice. So what I'm going to do is I'm going to plug in C2 and C1, where again C2 is that CDB plus CGD1 plus 1 over GM RD, and C1 is that CGS plus CGD1 plus GMRD. So what I'm going to do is I'm going to say V out over V in is this minus GM RD over, so my x squared terms gets a little bit complex, but let's go ahead and write that out. So then this becomes CDB plus CGD1 plus 1 over GM RD times CGS plus CGD1 plus GM RD times RG RD S squared. So then we have a plus CDB plus CGD 1 plus 1 over GM RD times RD plus CGS plus CGD 1 plus GM RD. And then this is times RG, and then that's my S term plus 1. So what I'm going to do now is I'm going to distribute this down here, and I'll copy and paste it for this term, just so we have a nice, clean, final equation. So when I clean this up, what I actually get is this CDB CGS plus CDB CGD 1 plus GM RD plus CGS CGD 1 plus 1 over GM RD plus CGD squared times 1 plus 1 over GM RD times 1 plus GM RD. Close that. And this is RG RDS. I hope this makes sense, how we get this. All right. If you have any questions, leave them down in the comment section below, and I'll be sure to get back to you. So let me go ahead and copy and paste this up here now. All right. So now we have a clean equation, and I did make a mistake here. This should be an S squared term. All right. So we have a nice, clean, final equation. So again, this here is my final equation. And essentially, I hope we can see that with Miller's effect, we took less steps to analyze this circuit, again, with that voltage divider equation at the beginning. And we got to a very similar equation, given we do the full analysis for the high frequency of a common source amplifier. Specifically, what I've done here is I've copied and pasted the equation from my previous video, where I did the entire high frequency small analysis. And we can see that the Miller's approximation, so it's missing a pole here, where normally this pole is extremely high in terms of my frequencies around 1.5 to 2 gigahertz. So we can ignore it. Another term that is missing in the final solution versus the approximation is this term here. This term here, which can be approximated to just being 1 because this is very close to 0. And then we're also missing this term here in the final solution. But again, this approximation, since CGD is normally very, very small in the picofarad range, this is also a very, very small value. And then lastly, in the final results here, we're missing this 1 plus 1 over GMRD. Again, this is a very small value, so this is going to be approximated to 1. So as you can see, Miller's effect can be a pretty good approximation, where it also helps us reduce the analysis that we have to do. And so the last thing I want to note is that if you consider V out over V in, again at S is equals to J omega, where omega is equals to 0, this is approximately minus GMRD, which is a similar result we obtain in the AC analysis of an ideal common source amplifier. Okay, now in the next video, we're going to consider the frequency response of the circuit, so please look out for that. And if you have any concerns or questions, please leave them down in the comment section below, and I'll be sure to get back to you. If you like the video, please give it a thumbs up, and please share the video with your colleagues and your classmates. And if you like the content of the YouTube channel, please consider subscribing. It really helps the algorithm. Thank you.